In today's lecture, we are going to discuss evolutions of quantum systems. So we state that an evolution of a closed quantum system is given by unitary operators. So let V be a Hermitian space of states of a quantum system. Or mathematically, so we just think that this is a complex Hermitian vector space, a complex vector space with a Hermitian scalar product. So we give a definition. An operator T from V to V, so a linear operator, is called unitary if for all U and V in the vector space V, so the Hermitian scalar product is preserved. So this means that TU with TV is equal to the scalar product of U with V. So this property basically states that operator T preserves the Hermitian scalar product. And in particular, so what this means is that so T transforms the standard basis into an orthonormal basis. Right. So simply, well, for the standard basis, we have that EI with EJ is equal to delta IJ. So it's 1 if I is equal to J and 0 otherwise. And if T is unitary, and so this preservation will tell us that T of EI with T of EJ is still equal to EI EJ, so which is delta IJ. And this means that this set of vectors will form an orthonormal set. And so this is another orthonormal basis. Now let us see what this condition tells us for the case of V being n-dimensional complex space with the standard Hermitian form. Right? So we have U with V. This Hermitian form is given by U bar transpose times V. And so TU with TV is then equal to TU bar transpose times TV. And so this becomes U bar, well, maybe I'll write transpose with the little t because we have capital T here. U bar transpose times T bar transpose times TV. Right? And if T is unitary, so these two things are equal. And so from here, so since this holds for all u and v in Cn, right? So this implies that this matrix is in the middle must be the identity matrix, right? So this tells us that T bar transpose times T is equal to identity matrix, right? And this is an exercise. So again, to do this exercise, so what you have to do is you have to take as u and v all possible standard basis elements, and then so one can prove this relation from here. And so then in particular, so the ramifications of this is that T is invertible. And so moreover, so we can see from here that the inverse of T is equal to T bar transpose. Right. So this is another characterization of unitary operators. So one can define a unitary operator as an invertible operator with this property. Now let us describe eigenvalues and eigenvectors for unitary operators. So we have the following theorem. So let T be a unitary operator on a Hermitian space V. Then, so A, eigenvalues of T are complex numbers of norm 1. So this means that eigenvalues are situated on a unit circle in the complex plane. And B, eigenvectors of T corresponding to distinct eigenvalues are orthogonal to each other. So we point out that this theorem is valid both in finite dimensional setting as well as in infinite dimensional setting. So let's give the proof of this theorem. So we start with part A, and we say that let V be the eigenvector. So TV is equal to lambda V. And so then, so we just, let's compute what is TV with TV. Right. So this equals to the scalar product of lambda V with lambda V. Now, so here we can pull out lambda from the second factor. And from the first factor, when we pull out lambda, it comes with a complex conjugation. So we get lambda times lambda bar times VV. And lambda times lambda bar is norm of lambda squared times VV. Right? And if T is unitary, this is simply equal to VV. Right? So here we use the fact that T is unitary, because unitary operators preserve scalar product. So TV with TV is equal to VV. And so we also note that if v is non-zero, then the scalar product of a vector with itself is non-zero because it's a real positive. And then from this equality implies that norm of lambda is equal to 1. Right? So this factor must be equal to 1. For part B, so we take two eigenvectors. So we have so Tu is equal to lambda u, and Tw is equal to mu times w. And so then let's consider Tu with Tw. So this is equal to lambda u with mu w. And so this is equal to lambda bar times mu times u with w. But, so what is lambda bar? So if norm of lambda is equal to 1, so then this means that lambda times lambda bar is equal to 1. And this means that lambda bar is equal to lambda inverse. So this can be written as mu over lambda times u with w. And if t is unitary, this is simply equal to u with w. And so if we take the difference, so then we get 1 minus mu over lambda times u with w is equal to 0, right? So, but if mu is not equal to w, right? So here we assume that mu is distinct from lambda. So then this factor here is non-zero. And if this factor is non-zero, so this tells us that the second factor, u with w, must be a zero factor. And this tells us exactly that the eigenvectors corresponding to distinct eigenvalues are orthogonal to each other. So let us state the spectral theorem for unitary operators. So a unitary operator T on a finite dimensional Hermitian space V is diagonalizable. So it has an orthonormal basis of eigenvectors with eigenvalues of norm 1. So this means that if we take the basis, the orthonormal basis in which a unitary operator is diagonalizable, then this unitary operator will look like e to the I alpha 1, e to the I alpha 2, e to the I alpha n, right, and zeros elsewhere. Right. So here, we use the fact that if lambda has norm 1, a complex number, then this lambda can be written as e to the I alpha, where So e to the I alpha by Euler's formula, this is cos alpha plus I sine alpha. Right? So if we take a unit circle in the complex plane, and so if we take lambda that sits at the angle alpha here, so this is the description of complex numbers with norm 1, then these complex numbers can be written as exponentials of e to the I alpha, where alpha is here is just a real number. Now, let us look in more detail at evolution of a quantum system. So here, so suppose we start with the psi 0. So this is initial state at time equals 0. Right? So this psi 0 is going to be a vector in the space of states, and so the norm of this vector is equal to 1. Then, so what will happen is that, so now if we want to find the state of a quantum system at time t, then so here we will have a family of unitary transformations, and this will be times psi 0, where so here so u of t is a family of unitary transformations. And so basically, so what we want to do is we want to control evolution of a quantum system. So in order to control evolution of quantum system, so what we can do is we can change this family. So this can be done by, say, changing the ambient magnetic field in which this quantum system is embedded. Or we can, say, have a quantum system at which we can shine laser beams. And so depending, so what is the intensity and the length of this laser impulse, so the evolution of a quantum system will happen differently. So basically, so this is the thing that we can control here. Right? And so we want to control evolution of a quantum system in some prescribed way. Now, the general scheme of quantum computation has 3 parts. So the first part is initialization. The second part is performing quantum algorithm. And the third part is measurement. So here, when we talk about initialization, so this means that we prepare initial state psi 0, right? So this could be some vector that we know in our space of states, or so this vector may depend on the input for our quantum algorithm. Now, so the quantum algorithm that's on the second step, so this is a unitary transformation. And let's point out that unitary transformations, because they preserve scalar product, they also preserve the length of a vector, right? So because the length of a vector is expressed in terms of a scalar product of a vector with itself. And so this guarantees that if the initial state had norm 1, then at each time, so psi of t will also have norm 1, right? And so at the end, we perform the measurements, right? And so we make an observation. So make an observation. And so here we have a probabilistic outcome. And so what's important for us is, so we should find such a unitary transformation so that we can infer some useful information from the result of this observation. So this means that so we need to arrange our quantum algorithm in such a way that we get a meaningful answer at the end with a high enough probability. In this course, we will need some basics of group theory. So there are two reasons for it. So one reason is to better understand quantum algorithms. And the second reason is so we need group theory to understand cryptography, because much of this course will be cryptography related. So let's give a definition of a group, or recall the definition of a group. A group G is a set with a binary operation of multiplication operation of inversion, so with a single argument, x inverse, and a distinguished element E in this set G. So this is called identity element. Satisfying axioms. So for all x, y, and z in the group, so we have the following three axioms. 1, x times y times z is x times y times z. So this is called associative law for multiplication. Then 2, x times identity and identity times x is equal to x. So this is the axiom of identity. And 3, x times x inverse and x inverse times x are both equal to identity. So here we have a definition of a group. Now let's give some examples of groups that are relevant for us. So here we have a general linear group. So we can take GLNR. So this will be n by n invertible real matrices. So here the operation, so x times y, so this is matrix multiplication. So x inverse is the operation of a matrix inversion, and the identity element is the identity matrix here. And so we know that we have associative law for matrix multiplication. So this means that this is going to be a group. So in a similar way, we can take GLNC. So these are invertible n by n complex matrices. And so then as a second example, we can take a special linear group. So which will be a subgroup in the corresponding general linear group. So we have SLNR. So these are real n by n matrices with determinant 1. Right? And so this set is closed under multiplication, because if we have determinant of x is equal to 1 and determinant of y is equal to 1, then this implies that determinant of xy is also equal to 1, because it's equal to the product of determinant of x times determinant of y. And so what we see is that the set SLNR is closed under multiplication and also closed under inversion, because the inverse of a matrix with determinant 1 also has determinant 1. And likewise, we can take SLNC. So these are complex n by n matrices with determinant 1. And again, so SLNR is a subgroup in GLNR, and SLNC is a subgroup in GLNC. So the next example is the one that's relevant to today's discussion. So this is unitary group. So UN is the set of n by n unitary matrices. So this means that, well, UN is the set of matrices T in GLNC. So these are complex matrices with the property that T bar transpose times T is equal to identity matrix. Now, let's prove a lemma that UN is a subgroup in GLNC. And so to prove this, so we make 3 observations. So 1, so first of all, identity matrix belongs to UN. So identity matrix is unitary, right? So because, so clearly identity transpose bar times identity is equal to identity, right? Then 2, so if we have x and y in UN, then so this implies that x times y also in UN, right? So we, by the way, we note that all matrices in UN are invertible, because from this definition it just follows that T inverse is equal to T bar transpose, right? And so then, so we need to verify that x times y is unitary. So what does it mean? This means that xy bar transpose times xy. So we need to check that this is equal to identity matrix. So now this equals, so when we take the transpose of the product, so we take the product of transposes in the opposite order. So here we get y bar transpose times x bar transpose times x times y. But x is a unitary matrix. So this means that x bar transpose times x is identity. So this is equal to y bar transpose times identity times y. And because y is unitary, so this is equal to identity. And so we see that x times y satisfies the definition of a unitary matrix. So this means that so unitary matrices are closed under multiplication. And finally, we need to show that the set of unitary matrices is closed under inversion. So this means that if X is a unitary matrix, then X inverse is also a unitary matrix. Right. So, okay, so let us just set S to be X inverse. Right. So what we need to show is that S satisfies this condition. So we need to take S bar transpose times S and show that this is identity. Now, here, so S is X inverse. So we have X inverse bar transpose times X inverse. Now, so here, so the transpose commutes with conjugation and commutes with the inverse. So this is the same as taking X transpose bar and then take inverse times X inverse. And again, the inverse of a product is the product of inverses in the opposite order. So this can be written as X times X bar transpose and all of this inverse. And so now, so we know that X bar transpose, well, since X is unitary, is equal to X inverse. So this is X times X inverse, and then take an inverse of that. And so this is equal to identity, because X is a unitary matrix. So we proved that the set of unitary matrices is closed under multiplication, inversion, and contains identity matrix. So this means that the set of unitary matrices is a subgroup in GLNC. So, and this means that this is a group itself. One more subgroup that is commonly used is called the special unitary group. So this is SUN. So this is basically the intersection of UN with SLNC. Right? So these are unitary matrices with determinant 1. And so because intersection of two subgroups is a subgroup, so this is a subgroup in UN. Unitary groups play a very special role in quantum theory. And just as a side remark, so I just wanted to mention that the standard model of elementary particles is based on unitary groups. So if we want to classify elementary particles, and then the group that we need is U1 cross SU2 cross SU3. And so here U1 is responsible for electromagnetic interactions. SU2 is responsible for nuclear weak force. And SU3 is responsible for quarks and strong nuclear interactions.